Good morning to one and all. By offering my humble pranams to lotus feet of His Holiness Jagat Guru Dr. Shri Shivaratri Rajendra Mahaswamiji and seeking the blessing of His Holiness Jagat Guru Shri Shivaratri Deshikendra Mahaswamiji. Myself, Vinisha Vijay, MSc Physics student, welcome all of you to the international seminar on Designing Ferrocene Nanoparticle Hybrid Catalyst for Enhanced Efficiency and Safety in Solid Rocket Propulsion, organized by Department of Physics, SJC, JSS Mysuru. Let us commence this wonderful event by invoking the divine. I request Ms. Duty, a MSc Physics student, to present the invocation. Sir?
I request delegates to come on stage.
Sorry for the inconvenience. I request all the delegates to come on the stage. Now, let us commence this wonderful event by invoking the divine. I request Ms. Duty, first year MSc Physics student, to present the invocation.
श्री गणनाथ सिंधुरावर्ण करुण सागर करिवदना लंबोदर लकुमिकरा अम्बासुत अमर विनोत लंबोदर लकुमिकरा सिद्धचारण गण सेवित सिद्धिविनायक ते नमो नमो लंबोदर लकुमिकरा अम्बासुत अमर विनोत लंबोदर लकुमिकरा सकल विद्या आदि पूजित सर्वोत्तम ते नमो नमो लंबोदर लकुमिकरा अम्बासुत अमर विनोत लंबोदर लकुमिकरा.
Thank you, Duty. Now, I request Dr. Madhusi, head of the Physics Department, to welcome the gathering.
Submitting my humble pranams to the lotus feet of His Holiness Jagat Guru Shri Deshikendra Mahaswamiji and His Holiness Shivaratri Rajendra Mahaswamiji. Good morning, everyone. So it's my humble, it's my privilege to welcome the delegates for this function. First of all, I like to welcome our Vice Chancellor, Dr. A.N. Santosh Kumar sir, in his absentia. I also like to welcome Dr. Dhanraj, Register, in his absentia. I also welcome Dr. C. Nataraju, Principal, SJC, JSSSTU, in his absentia. So I also today I also welcome today's President of this function, Dr. Mallu, Vice Principal, SJC, JSSSTU. I also welcome today's chief guest and also center of attraction of today's function, Professor Cesar Morale Verdejo from University de Universidad Bernardo Higgins from Chile, South America. So I also welcome head of the department from ISC, Shuprakash sir, head of department of chemistry, Kumar Swami sir, head of department of mathematics, PSK Reddy, and all the faculty members from different departments. And I also like to welcome all the participants, especially youngsters, all the MSc students and PhD students for this function. Thank you.
Thank you, sir. And I also welcome our beloved HOD, Dr. Madhusi, to this event. I request all the distinguished guests to inaugurate this event by lighting the lamp and offering a floral tribute to His Holiness Mahaswamiji.
ಇರಲಿ ಬಿಡು.
Today, we are honored to have with us renowned researcher, Professor Cesar Morale Verdejo, Bernardo Higgins University, Chile. I request our Vice Principal, Professor P. Malu sir. Now I request Dr. Madhusi to introduce today's chief guest.
Good morning. So it's a privilege to introduce the chief guest of this function, Professor Cesar Marelo Verdejo. So he has completed his graduation and PhD from Pontificia Universidad Católica de Chile. So later he did his postdoc from Argonne National Lab, USA. Then he worked at different places, and later he moved. He became assistant professor, then associate professor at Universidad Bernardo Higgins, Chile. So right now he is the Director General of Research, Innovation, Transfer, and Entrepreneurship at the same university. So he is a well-known researcher, and he works in the field of catalysis. So different catalysis, and he has published more than 60 papers in the Scopus Index Journal, and which has right now having more than 700 citations with a H index of 16. So it is very brief introduction. He is also a visiting fellow at different universities like in France, Barcelona, and other places. So this is a very brief introduction. And now I request uh, Malu sir to felicitate our chief guest.
We are honored to have with us the Vice Principal, Professor P. Malu sir. I kindly request him to present the presidential remarks for this event.
Offering my humble pranams to Sri Sutturu Guru Parampara, seeking the divine blessings of His Holiness Jagat Guru Sri Sri Sivaratri Desikendra Mahaswami Galavaru. Good morning to one and all present here. Dear dignitaries on and off the dais, invitees, my dear colleagues and participants. It's an honor to speak with you today on topic that stands at the intersection of nanotechnology, chemistry, and aerospace innovation. The development of ferrocene nanoparticles hybrid catalyst for solid rocket propulsion. First of all, I congratulate the program coordinator and head of the Department of Physics for organizing this impactful international seminar, bringing together minds from diverse domains to explore advancement in propulsion technologies is both timely and commendable. As we push towards more efficient, safer, and environmentally responsible propulsion systems, traditional single component catalysts are no longer sufficient. Ferrocene, with its excellent thermal and redox properties, offers a strong foundation, but at a nanoscale, its potential is truly transformative. By engineering hybrid catalysts, combining ferrocene nanoparticles with materials like graphene or metal organic frameworks, we can enhance combustion efficiency, reduce ignition delay, and improve thermal and mechanical stability. These advances lead up to 20% greater combustion efficiency, faster, more reliable ignition, and improved safety profiles for handling and storage. Equally important, we are exploring greenery ferrocene derivatives, helping move towards sustainable aerospace solutions. I hope you know today's speaker, Professor Cesar. He is a well-known chemist. I saw his profile. He having in his account 4 international patents related with this research work, and what we saw is credential. He is basically a chemistry person, so that's why I requested our HOD, chemistry HOD, and our colleagues also. Please inform to our students to participate, get the information, get in touch with this professor. Maybe in future, anybody interested do the research in this line, nanoscale, rocket propulsion and other things. Maybe he's a right person. Maybe you can choose him and his university. Maybe it is a benefited for you people. So in that context, I thanks Dr. Madhu Chanbasappa, invited him, a chemistry professor, to our university, and he is going to address his research work. Maybe it is a benefit for you people. He is along from Chile. He is coming here to your place. You can exploit. You can interact with him and get the details, and you share your interest with him. That definitely it is useful for you people. So in this seminars we observe, so of challenges we are going to observe, so many challenges remain: scalability, long-term stability, and integration to existing system. But through international collaborations like Professor Cesar and cross-disciplinary research along with chemistry, physics, and solid-state physics like that, we are well positioned to overcome them. In conclusions, ferrocene hybrid catalysts are not just improving rocket propulsion, they are redefining its future. Thank you, one and all.
Thank you, sir. Now, I request Dr. Mahesha to deliver the oath of thanks.
Good morning, one and all. It's my privilege to deliver the vote of thanks in this international seminar. First and foremost, I thank Vice Chancellor of JSSSTU, Professor A.N. Santosh Kumar sir, in his absentia. And I thank Registrar Professor S.A. Dhanraj sir, Registrar JSSSTU, in his absentia. And most importantly, our chief guest, Professor Cesar Morales Verdejo, and I thank him to accept our invitation and to be a part of this international seminar in our institute. And then I thank our beloved Vice Principal, Professor P. Mallu sir, to accepting our invitation and to be a part of our program. And I thank all the deans and the officers of our university, and they supported in all the way to happen this event. And I thank all the HODs of various departments. They supported us in all the way, and they visited today and participated in our program. I thank all the HODs and all the professors and all the various teaching staffs of various department and all the university staffs. And first and the most important, I thank our beloved HOD, Dr. Madhu Channabasappa, and he is the backbone of this event. Heartfully thank him to happen this event. And I thank all the staff and non-teaching staff of our Department of Physics, and also the master's students of our physics department, and also all the students of science courses. And I thank all of you to be a part of this event. I hope it becomes a very important and impactful session for all you guys, and you just make it useful for your future research work. Thank you, one and all. Thank you.
Thank you, sir. Now I request Professor Cesar, sir, to deliver his lecture on the topic Designing Ferrocene Nanoparticle Hybrid Catalyst for Enhanced Efficiency and Safety in Solid Rocket Propulsion.
So I also like to thank Yuraja for bringing Professor Cesar here, because he is the main coordinator who is behind this, his visit to India. And special thanks to Yuraja, Dr. Yuraja, who is also working at the same university.
Recording with my computer, yes. Yes, yes.
Should I have checked it? Not automatically.
So it's specific to
Yeah, I can screen share. We can screen share. So do we have it in pen drive? I don't think it will work with Mac OS.
yes, I have one. Yes, no problem.
You have want? You can. No, we can.
So that we can connect.
Ah.
I have a copy of PDF, but it's not possible to see in this, right?
Yes, yes. So you want to?
This PDF. I have this animation, but I think it doesn't work when I change.
Oh, you need for
but
You can copy it to me.
to what David? I don't know what is it. There.
No, okay, so let's this fine.
But I'm going to explain.
Yes, yes.
Yeah.
Try to connect it.
Okay.
Try to connect it 1 second.
Again?
Yeah, we'll try now.
Okay. It's not possible to
Yeah, I'll
press the search the source or something. Yes. Okay. 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 Thank you. I'm sorry for the delay. So, first, I would like to say hello, everyone. Hello, Vice Principal. Hello, the faculties, students. So, this is my first time in India. So, I think it's a really nice country. So the people is really friendly. Thank you for everything, and thank you of course for the inauguration ceremony. It's different. It's different. I like it. So maybe I can move this. Okay, because I sometimes I need to see the screen. Okay. So first I would like to start. Where is Chile? Okay, because I don't know how many persons have been in Chile, besides you, of course. Yes, one person and two with me. Nobody? Okay, yes. So Chile is here in South America. So this is a long land close to Argentina, and is from Santiago, the capital city, to New Delhi. The approximate or air distance is 16,000 kilometers, so it's really far away, right? So it took me almost 2 days to come here. Okay, so but it's really nice trip. So if we compare the both countries, so we can see the countryside between India and Chile. Chile is a little more long than India, and our language is Spanish. This is our mother language. Compared to you, you have many languages there. I know the Hindi, English, Kannada also. And our population is maybe nothing compared to you, right? So we are just a little more than 19 million, right? So, and also I would like to add this picture because my president, Gabriel Boric, came to India maybe 2 months ago in April, I guess, and he met the Prime Minister of India, right? So this is Chile next to Argentina. So we have different places. So we have the Atacama Desert, is the driest desert in the world, even more the Sahara Desert. So and we have the most sky clean in the world. Also, we have the ALMA observatory is in Chile. Is the in charge to study the universe. If we move to the middle of the Chile, here in the capital city, okay, Santiago, where I come from, so in almost half the population of Chile are living in this part. Yes? Okay. Okay. So this is a lot of farmland. So we export red wine. If you want to try, it's really good. And also, Eastern Island belongs to Chile. Okay. And if we move to southern Chile, we can find a lot of lake, volcanoes also. And Chile is the country closest to Antarctica. So you can see a couple of penguins in this picture. So this is my university. This is a private university. It's a small university. It was founded in March in 1990. This is a couple of, this is the main campus. A couple of pictures in autumn season. And this is the another campus. Is close maybe 10-minute or 5-minute walk. And this building belongs to the Faculty of Health and Faculty of Medicine. So we have just 4 faculties. So this is the faculties, and the total number of students is almost more than 9,000 students. We have also a 6 master program and 2 PhD program. So this is our research center. We have 8 research centers with different areas. So I belong to this one, to the SIPCA, so it's the initial. So we are working in different topics: nanotechnology, energy, biomaterials. On this material also apply to different with different applications like Alzheimer or muscular dystrophy. So we have also the astronomy center, public health, the history studies, and also the cybersecurity. So we have the PhD in science with mention in functional materials. So this is the call for this year. So this is the process ends in June 30, and the selection process starts in July, and then the classes start at the end of August or the first days of September. And we have just 4 vacancies because we are a small university, but we would like to increase this vacancy for the PhD students, of course. So this is the research line of the PhD in science. So we have synthesis, characterization of different materials, of functional materials, and also the computational method for design of these kind of materials, and the application of this material in different areas: chemistry, industries, medicine, so on. So what is the investment of UBO and also the allocation of external funds for research? You can see in the last 10 years or more, we are increasing now the investment and also the allocation of external funds. So this is impact our productivity. So we are increased, in the last 10 or 12 years, increase our productivity. We have more articles per year, of course. And also, if we have this kind of research, the basic research is possible to move to the next step, is the application of this research. So in this moment, we have a total, in the last 5 years, we have a total of 47 patent or innovation or invention patent with this kind of application research. And also, we create the first 3 technology-based enterprise of the UBO in different areas. This is the area for medicine, this is for health food for the head, and this is for preservation and restoration of antique cartography documents to ensure their long-term conservation. So this, of course, impact our position in the international ranks. So you can see in the last 6 years, so we are increase our position, right, in the different international ranks, QS Latam or Latin America, and also the UI Green Matters. So let's talk about this topic is about the design of first in nanoparticle hybrid catalyst for enhancing efficiency and safety in solid rocket motor, solid rocket propulsion. So you know more than me that rocket technology research is great, right? Significant to development of aerospace and defense industry. I know that you know that, me. So this is the reason that your country, reached to the moon in 2023, right? So landing near the moon's south pole. So if you remember the news, at the same time, Russia tried to do the same, but sadly Russia crashed to the moon, right? So congratulations for that. So it's really good news for you. So, and now, what is the space race? So now it's not limited the space race just to the government of the different countries. So this space race include the billionaire in the space. For example, Richard Brandt is the owner of the Virgin Galaxy, right? So Jeff Bezos is the owner of the Blue Origin, and also Elon Musk is the most popular because he is the owner of the SpaceX and Tesla, you know that. And thanks to SpaceX, today, according with the weather, it's possible to launch the first Indian on the ISS, right? According with the news. Congratulations again. So what happened with the Chilean space program? Okay, we have an early space program. So in this moment, it's possible to build different satellites with different proposals. So SpaceX helps to us, of course, through the bay, to put our satellites into orbit, right? So this national space program was founded 6 years ago. It's really early, and we have 3 steps. One step is build different satellites. Then they try to improve this construction of this building of the satellite for telecommunication. And the last step, this is I like it, of course, is try to launch a rocket from the land of Chile, right? And also put into orbit our satellites. So if the classification of explosive is for we can find different classifiers for explosive. So the most important is the high explosive and the low explosive, or it's possible to call propellant. So if you see what is the difference between each other is the velocity for the decomposition and also the direction of the detonation wave. For example, for the high explosive, it's the same way to the direction of the detonation of the products. So we call detonation. And compare with the low explosive, this direction of the burning is opposite to the direction of the burning of the product. So this is good for us because this produces the thrust in the rocket motor, right? So also we can classify the propellants in different states of matter, liquid or solid, and we are focused our attention or our research in the composite solid propellant based on ammonium perchlorate or AP. So this is animation. Yes, it works perfect. So you can see this is the part of the composite solid propellant, is the fuel, the solid fuel, and we have the initiator. The initiator starts the reaction, the decomposition, and this decomposition form hot gases. These hot gases pass through the nozzle and produce the thrust, right? So this is a Newton's third law of motion. You know, it's a classic law. And for chemistry, this is a really simple chemical reaction without consider the binder. And we have this in red, the gases, the hot gases, they produce the thrust in a rocket motor. So if we see the ballistic, the thrust curve, it's possible to have a relate between the burning rate and the pressure of the chamber, mean the chamber pressure, and also the pressure index or the pressure exponent function of the propellant formulation. So I'm chemist, so this is the reason we modify this part and also try to have the security condition between 0 and 0.5 in order to not get a explosion for the rocket, right? So we can get also the thrust curve. So this is the curve, and if we integrate the area under this curve, we can get the total impulse. And if we know the propellant mass, we can get the specific impulse. And also, finally, we can get the maximum velocity if we know the rocket mass and rocket propellant. So this is how it's possible to get a good rocket motor. So, if possible, to modify the burning rate, two options. One of them is decrease the oxidizer particle size, but this is a little restricted because if we have the ultra fine AP may cause explosion, so we don't want this kind of explosion. So the best idea is add a burning rate catalyst to the propellant. So nowadays are working in metal oxides and also nanometal particles, metal chelate, and ferrocene derivatives. So why is so important the ferrocene? Because if you compare different iron derivatives, the ferrocene show the best development to different percentage. So this corresponds to the around 3 or 5% in mass, of course, to the composite solid propellant, according with the different ingredients. So, because it's quite difficult to prepare, or it's costly, it's expensive to prepare a fuel of the rocket motor, so it's more easy to check or to test the different burning rate catalysts with the DSC curve. So what is the reason? Because the burning rate catalyst on the thermal decomposition of AP has a close relationship with the combustion process of the composite solid propellant. So the idea, so you can see the DSC curves. So the DSC curve, the differential scanning calorimetry, you can see in black the profile curve of the AP, just AP pure. So, and we can see two temperature decomposition, lower and higher. So when we add burning rate catalyst, it's possible to merge both and increase the heat release and also achieve the high temperature decomposition of AP. And that means that we can get a good burning rate catalyst because they have a close relationship, this thermal decomposition with the combustion process. So what is the advantage to use the ferrocene derivatives? Because they have a better microscopy of homogeneities in distribution, also a good compatibility with organic binders, but also they present some drawbacks. So is sublimation loss during processing, migration of the store, poor aging, irreproducible properties of the propellant, reduce the service life, change the design and burning parameters, and the unexpected explosion. So what is the idea to improve this one, or the strategy to retard or eliminate the migration tendency? This is the migration mechanism of the ferrocene. So one idea is create or synthesize different polymer derived from ferrocene, or attach ferrocene in the polymer like HTPB. Or the other strategy is the create ferrocene with polar groups attached to the ferrocene, okay, in order to retard or eliminate the migration tendency. So we are working in different burning rate catalysis, the ferrocene derivatives, mono, homobimetallic, heterobimetallic, or nanoparticles, iron, copper, and coordination complexes like iron, copper, and ruthenium. So I'm going to show some result that we already have and what happened next. So our first proposal was to increase the molecular weight, because this is the right to try to retard the migration tendency. So this one, when we add the methyl groups, so it's possible, of course, to get a high molecular weight and show the evaluation of migration tendency present a lower migration tendency, right? So this is the test with the difference burning rate catalyst with AP, the DSC curves at different percentage, and also it's possible to get the result because when it's possible to get a relationship between the oxidation potentials of this catalyst, so is according with the catalytic effect. So if you can see, we have a lower oxidation potential, of course, because according with the mechanism, it's possible to transfer that electron to start the decomposition of AP. So we test the different burning rate catalysis, in this case with different spacer ligand with different distance between the iron, and we get this one. This one is big, it's a really big or high molecular weight. So of course no migration tendency, but the problem was the catalytic effect. It wasn't the best. So what happened here? If you see, we compare, for example, the distance. So increase the distance, number 5, and also reduce the oxidation potential and reduce the catalytic effect. So this confirmed that this kind of reaction starts with electron transfers first. So we tried with different burning rate catalysis. In this case, we change the metallocene to the other side. So you can see we tried with cobalt, with nickel. This manganese tricarbonate is isoelectronic with the ferrocene, so we test also. But in this case, we didn't find a tendency. So we test now with the. If you remember, I said this is isoelectronic with the ferrocene, so we test with different metallocene in the opposite side. This is the reaction, this is the test with the DSC curve. So in this case, we see a tendency according with the oxidation potential. So this with the cobalt compounds, we have the lower oxidation potential and correspond to the best, according with this one, the best catalytic effect, and also the best heat release compared with the other one. So the next proposal was, we already know the ferrocene is a good burning rate catalyst, so according with the different articles, and this part, the nitrogen-rich compound, is good for prepare different derivatives in the high energy materials. So we prepare, this is the synthesis, we get the crystals. This was really difficult, it's not too soluble, so I missed some line here. So but it's possible to get the spectrum, the NMR spectrum for this one. And also this kind of system is possible to add alkyl groups and synthesize the ionic liquid. So we have, this is the ionic liquid for the monometallic compounds and the ionic liquid for the bimetallic compounds. So, and also we reduce the melting point, of course, and we get the NMR characterization for each one. So what about the anti-migration analysis? So of course this is double. We have two ionic liquid in this same molecule, so also more interaction with the ammonium perchlorate. So we have the lower migration tendency compared with the other one, but according with the catalytic effect is not the best. So the best was the monometallic compound. So what happened? According with the possible formation or the mechanism for this kind of system is the decomposition of the ferrocene and form the nanoscale materials. And we in that moment we thought, what happened if we check the usage span after the thermal degradation of AP? So we did it, and we found different nanoparticles according with the size of the monometallic, bimetallic, or the ionic liquid. So this is the resolution is not good, but maybe you can believe me that this is around 6 nanometers, this is 7 nanometers, and this is the 16, and this is 17 nanometers. So we can get the particular size, lower particular size correspond to the monometallic compound. So according with this one, we can see also, and compare with the oxidation potential, we can get the best heat release and also the best catalytic effect, and we propose this mechanism to with our or the best burning rate catalysis form the nanoparticles, and this heat release promote the decomposition of AP and also accelerate the electron flow. So this was published in 2023. So maybe you are after when I show you said why you don't try the nanoparticle, right? Like burning rate catalysis is if this is part of the mechanism. Okay, see, in parallel we did it. So we have the support of the U.S. Army in this case, and we test the copper nanoparticles supported on reduced graphene oxide. But in this case, the nanoparticles is better without the reduced graphene oxide, because this graphene oxide act like retardant in this catalyst. So we test the magnetic nanoparticles, so it's possible to functionalize the surface of the nanoparticles. We have nanoparticles around the 6 or 7 nanometers, the size of this size, and we test with different nanoparticles with different functionalized groups, and also we can get a good result with the heat release and also achieve to the thermal decomposition of AP, and also lower activation energy. So recently we are working in the ferrocene nanoparticle hybrid catalysis. What is the reason? Because you already know that the ferrocene is a good burning rate catalysis. So we show the superparamagnetic nanoparticles is also good. So what happens if we combine both? So increase also the heat release and also present better catalytic effect on the thermal decomposition of AP. So after all, we thanks to the armament factory of the Chilean army, so we test the burning rate. So we prepare the small rocket motor, and this is the rocket plant mixed pot, and this is the K-round. This is the small rocket motor, and this is the pressure transducer. This is how it looks when we set up before the test. So I hope it's possible to see. So this is the video, and this is the video, and you can see, okay, this is maybe 3 seconds or 4 seconds. This is enough to know is our burning rate catalysis is good or not. Okay, so we get the curve, the thrust curve for this one is neutral, and also we get the burning rate at different pressure. So it's possible to use if you remember the equation, the burning rate, and you can see the base is without the catalyst, the burning rate catalyst, and propellant ones correspond to the common burning rate catalyst used is the ferric oxide, and we can see both are really similar. This is our best burning rate catalyst, and you can see it's really similar at different pressure, the burning rate. But what is the most important is the pressure exponent, because when we add the common burning rate catalyst, the pressure exponent increase, right? So this is, if we want to increase the burning rate, this is going to increase, so this is dangerous. But in our case, happen opposite, right? So decrease the pressure exponent, so we can add more, in this case, more a burning rate catalyst without the problem to, or the risk to explosion of our rocket motor, right? So what is the mechanism of this? We until now we don't know. So maybe, so this is the idea we can discuss. So maybe if you have some ideas, you can give me and start a new collaboration about this science. So what is the application? So different application. In this case, our Chilean Army is for the chaff rocket. So this chaff rocket is using for the Navy, the Chilean Navy, to form this curtain of fume in case of war, of course. And we are working, because I already told you that we are working in the build to different satellites, but we are working into this kind of research to create a micro proportion. What is the reason? If you see that one, yes, this is the normal bus, and put into the orbit different satellites. But nowadays we have a lot of junk in the space, right? So the idea is when some satellite doesn't work, so you have to wait until the satellite fell to the Earth, so you can use this micro proportion to deorbit the satellite in case that it doesn't work. Okay, like this, for example. So this is our research group. We have a multidisciplinary research group from chemistry, from engineering, and different University of Chile, and also different student, PhD. This is the Juby. He is working with me. He has the postdoctoral position. And also, we are working with the Chilean Army. We have a co-researcher and a student for the Chilean Army, and also we have the co-researcher from the Air Force of Chile and the Chilean Navy. So I would like to thanks to this is in Spanish, I'm sorry. So I would like to send thanks to my university, the research center, all the National Agency of Research and Development of Chile, belong to the Science Ministry with different projects, also the US Army, and of course the Chilean Army and Air Force Chile and the Navy Chilean give me the support for this kind of research line. So what is the research opportunity in Chile? So it's possible. I mean, I would like to start a research collaboration. So this is we can talk. You have my email. If you are interested, you can send me an email, please. And also the academic exchange programs. You can visit Chile. Okay, I know it's really far, but it's just 2 days. It's not too far. So, and also the possibility to be associate research of the UBO, my university. For the student, it's possible to research opportunities are available for graduate student, PhD program, as an exchange program for higher education student, and for the young researcher, we are offering a postdoctoral opportunities. So we have two options. One is the postdoctoral of the university, and the other is applied to the postdoctoral position with the financial with the Chilean government. Okay, so if the problem is Spanish, we also have courses of Spanish, but it's not too difficult. But it's not a problem if you go to the university. Everybody speak English is not a problem. So maybe you can ask to Julie about his experience. So that's it. Thank you very much for your attention. And if you have questions,
How did you assess the stability of the catalyst?
the stability of what?
Of the catalyst?
What?
Procedure you have used for assessing the stability of the catalyst?
The stability of the catalyst. So this one, for example, in the ferrocene compound are really stable to air. So maybe the synthesis is under nitrogen, but they are really stable to air. So we don't have to. We can live in there maybe 2 months, six months is okay. So, but with the idea, thank you. Remember me because I forgot to mention. The idea for this one is when you combine both, right? We already know that both are good burning rate catalysts, but we can also I forget the word, but we have the drawbacks for the migration tendency. So if we attach to the nanoparticles, so it's possible to avoid that migration tendency, right? Retard or eliminate. But in the case of the nanoparticles, so the nanoparticles, the problem is the agglomeration, right? The agglomeration problem. So in this case, if we add this ferrocene or different ferrocene, it's also possible to avoid this agglomeration. So this is I forget to mention. Thank you very much for your question. Yes, this is the idea. Why we are working now in this hybrid catalyst.
And another question. We are using the catalyst because we are creating a high pressure temperature condition during the burning process.
Mm-hmm.
And the catalyst will also disperse here and there. Is there any possibility of recovery of the catalyst and reuse of the catalyst? Have you made any studies regarding this?
Yes, this is a good question. So yes, I mean, is the next step, because nowadays, if you are going to use this for defense, of course you don't care, right? Because you. But if you want for the space program, yes, of course, you want to recover everything and they recycle everything. So yes, it's possible because we are trying to test for example, after the burning test of this one, try to see is lost or not the superparamagnetic properties of this catalyst. So, but we have tried just a little amount, so it's not enough to test that. Okay, so this is we are working in this moment. Okay, thank you. Yes.
What is the stereochemistry or conformation of the kerosene used? Everywhere you have shown staggered conformation of this one, ferrocene in all your reactions. If it's not possible to get eclipsed form of ferrocene, is there any effect of that on the propulsion rate or burning rate?
So you are talking about the
Stereochemistry of ferrocene.
which one?
Any of the this one only.
Okay.
There you have mentioned both all the in two reactions also it is staggered conformation of ferrocene. Staggered and eclipsed. That you have mentioned.
The conformation is we have the isomer.
Yeah.
Isomer. Yes, it's possible to get a rotation here. Yes, of course.
Is this if it is?
But according with our NMR, it's really clean. So you can see. Let me show you the other one, the second, this one. So you can see, yes, maybe it's possible here to see the other isomer, but in our case we see just one isomer. But maybe it's not this isomer, but I just draw like this. But we get just one isomer. Yes, it's possible yes.
Have you checked your catalyst with other aviation fuels?
The what? Sorry?
Have you checked this catalyst with other
another type of fuel. Yes, we now we are working. I don't show it, but are working to the because it's not easy to work with AP because it's restricted for us. So we synthesize the different catalysis and we pass this catalysis to the Chilean army. So, but we have to wait according with their time, right? So the result. But so we are working now in the candy propellant. You know the candy propellant? Candy, like something sweet, sugar, and the potassium nitrate. So yes, because it's more cheap or inexpensive, and also it's more easy to buy or get from the fertilizer, right? So we are working in this. Also, we have project in this kind of things, but we don't have all the result. This is the reason I don't show everything. This result. Maybe the next time I can show you. So, but yes, we are trying the same or different burning rate catalyst to try to see what happened and compare this rocket motor made with the composite solid propellant based on the AP compared with the other one with the candy propellant, you know.
So it works with the kerosene means, obviously it works with C4 to C9 fuel also. I think it is better, sir.
Oh, sorry.
It will be a better catalyst for C4 to C9 fuels, aviation fuel,
Uh-huh. Oh,
than this fuel.
sorry, I can hear very well. It's my problem. It's not you. Sorry. Maybe you can come and tell, or maybe someone can do.
No, it's okay, sir. It's okay.
It's okay? Okay, no problem. Yes, we can discuss later. Sorry. Don't be shy. You can ask if you want to go to Chile. Yes. Yes, it's solid form because it's more secure. Increase what? No, but there is a. You're talking about. Let me find it. This part, right? So yes, the idea is to keep the mass or the ratio between this mass the same. So we can add a little amount, but remember it's a little amount of the burning rate catalyst. So this is it doesn't affect the mass of the propellant. But the idea is increase little because if you remember, it's another way. Is the ingredient is 3%, you know? Yes. So this is or 5 is the maximum. So the idea is increase to 5 and see what happened if according with this relation. So, where is it? There. Okay. You're welcome. Yes.
Nowadays, researchers are working on antimatter rockets and nuclear rockets. How this is unique than
For the nuclear.
nuclear rockets? Nuclear rockets and antimatter rockets.
Sorry, can you?
Antimatter and nuclear rockets.
Antimatter. Oh wow. Oh, okay. I'm chemist, and from this antimatter is a little complicated in this moment. So no, I have to not try to. I mean, I know it exists. I read it, but I know about this type of topics.
What's the specific impulse value of this?
I'm sorry.
What's the value of specific impulse?
The specific impulse is around. Don't remember. Is 100, 120, maybe. Yes. This is the reason that we are working with the candy propellant because the specific impulse for candy propellant is lower. You know, so we can add different burning rate catalysis So we try to increase and maybe same like composite solid propellant.
Is there any challenges in scalability of this?
Can you scale up? Like, is it possible?
Yes, I mean in this case, yes, it's difficult because you have to prepare a lot of burning radius, but it's scalable. So this is the reason also we are working with the super paramagnetic magnetite nanoparticles because it's more cheap to prepare and it's scalable.
Thank you.
You're welcome.
So, any more questions? Okay. So, if there is no question, let us thank Professor Cesar for his wonderful talk. So, thank you very much for taking your time to be with us.
Thank you.
And I also extend our invitation. You please come back again.
Sure.
Maybe next time when you come here.
Yes.
So we would like to have.
I would like to come.
Yes. Thank you. So thank you all for. So we'll take a photo.
Okay.